Yeah, so we will start with the just a quick recap of what we did in the last class. So essentially, we were looking at some how the two main weaknesses or limitations of the Bezier were overcome by the spline, and also that some interesting properties that result two limitations. The primary one was that the degree, because of the recursive definition, right, in K, right, as you go from K, given K to 1, we add a term in U every time in every step of the recursion, and therefore at the end I will have K minus 1 power on U, and therefore the degree of the curve is always K minus 1, and so that takes care of the first requirement. And the second requirement comes up from the fact of the way the recursive relation is defined, that n ik is always defined in terms of n ik minus 1 and n I plus 1 k minus 1. And therefore, the development of the basis functions that are non-zero takes sort of an upper triangular matrix, as it were, starting from the one basis function that is non-zero at the lowest level, which is j equals 1, right? And that also sort of led us to conclude that there are k basis functions that are non-zero, right? So you can see this here, and somehow, just like in the board, even on this pad, I'm not able to write in a straight line. But in any case, you hope you are convinced that this is indeed an upper triangular matrix, and this is the kth level basis functions that are non-zero, and there are k of them. You go from j minus k plus 1 to j, and so the total number of terms is so many. And we also sort of use this to plot the other triangle, which is the, in how many intervals, right, will njk be non-zero. And so this is the first interval for which we did it. And then as we keep sliding to the right, the last one where njk will appear is j plus k minus 1. And then again, there are k intervals in which the basis function will appear. And if the basis function appears only in k, the same number of segments will be influenced by the corresponding control point. And so those are the two interesting sort of attributes of the basis function definition in the case of the B-spline that gives you the second property, which is the local control, right? In some sense, it is not completely local. It is reflected, is restricted to k segments. But we have also seen that there are n minus k plus 2 curve segments, right? And therefore, the remaining of them are unaffected by any change in a given control point. We then also saw the types of knot vectors, and the one that we are interested in is the one where the first k and the last k repeat, right? The first k knot elements are always 0, and the last k knot elements are always n minus k plus 2. And you go from 0 to n minus k plus 2 in an integral fashion to complete the n plus k plus 1 terms inside in the knot vector. Okay. That's a specific one defined for a particular attribute, and you will probably infer it from the figure, but we will also state it again later. But the middle curve here is the one that corresponds to this knot vector that we have defined, where the last 4 and the first 4 repeat. And so for the given control points, right, 10 control points, remember we had made a mistake in the counting last time. So this is the knot vector that corresponds to the case here, where k is 4 and n is equal to 9, and that's the number of segments that you get, and you can see that. Okay. And this was a picture to just not this one, sorry, was the last thing that we did, where moving a single point affects, as we said, only the first few segments, the remaining segments starting from this highlighted endpoint remain unchanged, right? So you have 1, 2, 3, 4 segments or 5 segments that are not affected by this, and only the first 3, 1 or the first 2 only are affected because of this thing moving, right? And that's the other point we made, that the assertion of k control points and k segments are effective far away from the 2 ends as far as this particular knot vector is concerned. There's another example here where again you have moved a point P4, and you can see that the segments 1 and 2 are not affected, then 3, 4 and 5 are affected, and the last one 6 is again not affected, right? And this is an interior point, so it shows up in 3, and in this example, of course, k is also 3. It's a quadratic curve, and therefore there are n minus k plus 2 segments. Let's see what is n. N is 7, so you have a number of segments is 7 minus 3 plus 2, so that makes it 6. So let's count if we have 6. So there's 1 here, 2, 3, 4, 5, and 6, right? And the ones that change are clearly the segments number 3, 4, and 5, and the remaining remain unchanged. Okay. So this is what we had done in the last class. So I'll just stop for a minute now and check if any of you have any questions or comments or doubts in the material so far. Yeah. Okay. If there are none, then we need to proceed ahead, right? And what I wanted to do was to look at one other question that we should have asked. Remember, we had shown these parameters that have to be defined for, yeah, here, right? For the B-spline curve, right? Now, the number n and number k, we said, are parameters n and k are not related to each other. Okay, meaning that you can choose n independent of k, which is, of course, one of the desired things that we were asking. But let me ask you one question here now, which is that what is the smallest value that k can take? Meaningful value. Any answers? Or guesses, choices?
2.
2. Okay,
2,
and the reason for your choice is that
2 minus 1, 1. So order, exactly. I think order cannot be there.
Yes. So you basically are saying that the degree 1 is a linear curve, as it were, a straight line, and that's the sort of the lowest that you can go. And indeed, the smallest value k can take is 2, right? So if I were to put an interval on k, the smallest value it can take is 2. Note that if k is equal to 1, then your degree is 0, which means that you are not having any curve at all, right? It's just a bunch of points. So we don't consider this. This is the smallest curve, I mean the lowest order curve that you can expect, which is degree 1, order 2. Okay. Now, given that you have already made a choice on n, what is the largest value k can take, or is there a limit on that at all on that? So what should this second term be here? Do you think it can be, it is restricted, or you don't need to restrict it?
Don't need to restrict it.
Don't need to restrict it. Okay, that's one choice. Anybody think the counter opposite of that?
I think there must be a limit.
There must be a limit. Okay. Obviously, because I have put a bracket here, so I gave the game away.
It's a square bracket, so I guess.
Yeah, otherwise I wouldn't have bothered to put the bracket there. Okay. Anyway, I think you know the answer. There is a limit, and I think the first person who responded is in some sense right, because we had said earlier that there is no connection between the two, which is true. I mean, you can choose n independent of k, But as it happens, right, the choice of k is confined by n, right? Now, if you think about it, why is that? Why do you think k is restricted by n? If you go back to your original curve expressions that we were writing, right? Remember, we were writing that P of u, just for you to recall here, 0 to n ai u power I, right? This is the basic polynomial expression, right? Here also we are going to get polynomials in the case of the spline, but this is the most basic polynomial expression. But the reason I wrote this is so that you can see the connection between the degree that you have chosen and the number of terms that you need here, right? So if you choose n, then I must have a0 to an ai's here, right? N plus 1 ai's must be defined. Otherwise, I cannot fix my curve, right? And anything more is useless for me, and anything less, I have not specified my curve fully, right? I hope you appreciate this, meaning that in the case of a straight line, my expression will look like this, and therefore I need to fix both of these to be able to define the line. Okay, so in some sense, the same thing applies here, right? Though with a slight difference, right? The relationship is not so straightforward. But I hope you can appreciate that there must be some connection, between the degree, which is what k is specifying, and the number of points that I am specifying for the control points. Correct? Meaning that if I have specified n points, what is the largest degree that the curve can take? That must be fixed, right? I know this person is a little insistent. So let me just see if I can. Okay. Anyway, the person has stopped calling. So the degree is related in some sense to the number of coefficients that you are prescribing, right? So if my number of coefficients that I'm prescribing is n, what is the largest degree? What is the maximum degree that you can have? So if I have prescribed n plus 1 points, the largest degree can only be n, and therefore the order can only be n plus 1. That's one way to look at it. Okay, that if my degree is any more than this, any more than n, right, then I cannot have n plus 1 terms define that curve. I'll need more degrees of freedom to fix that, and I don't have that many here. That's one way to look at it. The other way to look at it is, remember when we defined the knot vector, we said that the number of segments in the curve, right, is how much? N minus k plus 2. Okay. So what's the smallest number of segments that you can have as k increases? What is happening to the number of segments for a given n? Is it increasing or decreasing?
Decreasing.
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 Exactly. And what is the smallest value of the number of segments that you can have for your curve?
1.
1. Yeah. So you can solve for n. N minus k plus 2 equals 1, and therefore k equals. That's the other way that you can arrive at this number. So what have we done? What we have said right now is that while there is no connection between the degree of the curve, which is specified by k, and the number of control points, it is not a precise statement, right? They are not related in the general case, but at the same time, you are not free to choose any k given an n and given k, choose any n, right? There must be a band, and that band is given by this, that k will always be between 2 and n plus 1. You cannot choose a k lower than this. Of course, it doesn't make sense. And you cannot choose a k higher than this because you don't have the freedom to define that curve, enough degrees of freedom to define that curve, coefficients to fix the degrees of freedom. Okay, so that's something that you need to keep in mind, that k always goes from 2 to n plus 1. Of course, you choose it and then it remains chosen. Then the band doesn't matter. If you choose k to be 3, you're done, right? Then as long as your n is more than 4, it cannot be less than 4. That's all that this is saying, right? So, sorry, 3, n must be 3. So if you, for a given k, you can similarly write what n must be, right? The smallest n that you can have. So just like the largest k for a given n is n plus 1, the same way the smallest n, right, for a given k is how much? Again, you can use the same expression and flip it, and this will become k minus 1. So your control points can never be less than this, and your order can never be more than this. So that's the bound that you need to keep in mind. Okay. So that's one point. Now let's go back and look at the curve itself, right? And we have not done, see, all this discussion, remember, I hope you appreciate this, is that all these discussions about the local behavior, the degree being defined by k, and this k control points controlling segments, all of these have been done without you actually having to evaluate anything here. Right? Just from the form of the relationship and the definition of the basis function, we have been able to conclude all of these. Right? You have not had to write any expression at all. But now the time has come to at least look at what the expressions look like. And this is where as I said, it was easier for me to write it down. So I will save this as a PDF and pass it on, except that I think I have made a mistake here. So I have to fix it first before I pass it on. But I'm just going to go through this because I know the answer, though I don't know what mistake I have made, but maybe one of you can catch it while I go through this. So what I want to do here right now, and this is not something that you need to do on a daily basis. OK, this is not something that you need to know at all, except that you should be aware that this is what is happening in the construction of the curve, given the inputs that you have given. OK, so a simple example, k is 3, therefore degree is 2. And I have 4 control points, therefore n is 3. And you know that it is satisfying all the conditions that we had just discussed, right? That n at best must be greater than k minus 1, it is, and k must be less than n plus 1, and it is, right? And therefore, we are all set, right? And once you know k and n, we can also write down the not vector by inspection. First k elements are 0. The last k elements are n minus k plus 2, which is 2. And in between it goes integrally, and that's all we have. Now what this means, we saw this in the last class, that the not vector basically splits your parametric interval, which is 0 to 1, into number of segments. And the number of segments are these, 0 to 1 and 1 to 2. Now, though I have said 0 to 1 and 1 to 2, right, I have written here below that you can normalize this by dividing it by 2, and it becomes 0 to half and half to 1, in which case it becomes consistent with our accepted protocol that u will be between 0 and 1. Right? But for the purposes of this derivation, I am not going to use the fraction form. I'm going to use the regular integer form. But both are the same because the not elements, they appear in ratios in the derivation of the curve, and therefore this normalizing division will cancel out, and so you should not have any effect in your calculations. Okay, so my interval is 0 to 1 and 1 to 2. The curve, of course, goes from 0 to 2 or 0 to 1, as the case may be. Right? So this is another thing that you should keep in mind, that in terms of the not elements, the interval of interest to you is always xk minus 1, xn plus 1, right? So this is xk minus 1, and this is xn plus 1. So x2 to x3, x3 to x4. That's the not interval of interest to us. So how do we generate the curve? Well, we do it segment wise because this definition is there for given interval of u. In this case, I first take the interval 0, u1. 0, of course, corresponds to x2 and 1 corresponds to x3. And therefore, from the definition, we know that n21 is 1, right? Because this is x2, right? And so n21 is 1. All the other ni1s are 0. So nj1 equal to 0 for all j not equal to 2. We don't have to worry about it at all. Okay. Having done that, we can now move on to the next step. Before that, I forget. Yeah, I have also written down the set of non-zero basis functions here, right? For this case, where u is between 0 and 1. n21 is 1, and therefore n12 and n22 will be defined non-zero. And because n12 is non-zero, n03 and n13 will be both non-zero. And n22 is non-zero, therefore n13 and n23 will be non-zero. So those are the only non-zero basis functions that we need to worry about. And so I calculate this now, and this is again just so that you feel comfortable. I have applied the formula as I have seen it. Now this is a little difficult to say this because, as I said, I don't seem to have the right result, but maybe I have made some mistake in algebra somewhere that you can catch. Okay, so the expression is u minus xk by x k I plus k minus 1 minus xi, right? And n I k minus 1. So that's what this is. So u minus xi I is 1, I plus k minus 1 is 2, and xi and I k minus 1 n11. But this is not, is 0. So therefore, I don't have to worry about evaluating this side. I go to the next term, which is xi plus k, which is 3 minus u by xi plus k minus xi plus 1. Right? So k is 2 and I is 1. Therefore, these are the terms I get here. n21, of course, is 1. And therefore, I plug in the value of x3. x3 is 1. Therefore, this becomes 1 minus u. And like that, I write down n22 as well. In the case of n22, the first term is defined, the second term is not. And again, I get some function. And as expected, the power in u is 1 less than 2, right? The k is 2, so I hope to see linear terms here, and that's what I get. Then I am ready to calculate the next row of k equals 3, which is done here now. And again, I'm using the same expression, except now I is 0, k is 3, right? So u minus xi, x0, I plus k minus 1, so 3 plus 0 minus 1 is 2, and ni k minus 1, but this is not defined, so this drops off. This is xi plus k, so 3, I plus k minus xi plus 1, and n12. n12 we have already calculated here to be 1 minus u, and therefore this becomes 1 minus u whole square. And that also pans out because k is 3, I expect to see a quadratic term here, and indeed I get a quadratic term here. Similarly, I can calculate n13. Here I is 1 and k is 3, therefore x1, xi plus k minus 1 is 4 minus 1 is 3, and so this follows, and k plus 1 and I plus 1 in this term. And in this case, both the terms are non-zero, therefore I get an expression that looks like this. Again, each term is quadratic, so overall that condition is satisfied. And lastly, the n23, where I is 2 and k is 3, so that's the expression, and that's the term, u squared by 2. So I can write my func curve in the interval 0 to 1 as p0 1 minus u square, that is p0 n03, that is the first term here, plus p1 n13, which is this term here, and lastly p2 n23, which is this term here, and that's what I have written. Okay, so this looks fine. I actually had a problem with the second segment. I don't seem to have gotten it right, and you can check this out. But I follow the same procedure again. Now the interval is 1 to 2, right? You go from 1 to 2, and this is x3, and this is x4, and therefore this is a non-zero term, and the basis functions that are non-zero are shown here. All other basis functions are 0. Only these 6 are the non-zero basis functions, right? And you go through the same exercise again, right? N2, 2. So I is 2 and k is 2. So this is the expression. This is not defined. This is I plus k minus u, I plus 1. And N3, 1 is 1. And therefore, I get 2 minus u. X4 is 2 and X3 is 1, right? So that's what you get. N3, 2, same way, you know, I is 3 and I plus k minus 1 is 5 minus 1 is 4. And that's the expression you get. So X3 is 1. So u minus 1, 2 minus 1. So this is u minus 1. Again, it checks out. I expect linear expressions and I get linear expressions. And same way you do it for the next curve. Sorry. I moved a bit fast. Let me see if I can get my mouse back. Yeah, here. Okay. And so the last step is for k equals 3 now. And so you do this for n1, 3, right? I don't have to worry about this term because n1, 2 is 0. And for this is I plus k and I plus k minus I plus 1, xi plus 1, and n2, 2. n2, 2 is already derived as 2 minus u. So this term becomes 2 minus u whole square by 2 because x4 is 2 and x2 is 0. And then I calculate the second term, which is second basis functions n2, 3. Again, I is 2, k is 3. Therefore, you know, this is x4 minus x2. And this is I plus k and I plus 1. And that's n3, 2. And both are defined in this case. So I have 2 terms. The first one is this is u by 2 minus 0. So that is u2. And n2, 2 is 2 minus u, so that goes here. And the second term is x5 is 2, so 2 minus u by 2 minus 1. And n3, 2 is u minus 1, so that's the expression I get. U by 2 into 2 minus u plus 2 minus u into u minus 1. The last term, and this is the one where I think I'm not getting the right term, so maybe you should focus on this a bit, is n3, 3. And so I get I is 3, so u minus x3. Aha. That is why I was wrong. Sorry, I got it now. Fine. I can fix it. This is u minus 1. So it's good to explain things. I don't know how many of you saw the mistake I had made. That is that. Okay, so I was saying that this is x3. So u minus x3, but x3 is 1. Therefore, this is u minus 1. And n3, 2 is also u minus 1. Therefore, this becomes u minus 1 whole square. And therefore, the expression for 1 to 2 is p1, n1, 3. n1, 3 is 2 minus u whole square by 2. p2 into n2, 3. Right, and that is this expression u by 2, 2 minus u plus 2 minus u into u minus 1. And the last one is this. I'll correct it now. This is not there, that is there. Okay. Now I write them side by side, and of course I have to correct this. I hope I have not saved it as an image. Okay, so fortunately I didn't make that mistake. And so this is u minus 1 whole square. Okay. Now, I'm not expecting you to derive this for any curve anywhere, right? Yes, this is just so that you know how it is done, right? The interesting parts are now, right? So first point is that I have what is the input? Let me just construct some dummy case. As I said, the n is 3, so I have 4 control points: P0, P1, P2, and P3, right? And my parametric interval 0 to 1 is now broken into 2 parts, right? So I have one that goes from 0 to 1 and the other one goes from 1 to 2, or 0 to half and half to 1, whichever you want to see it. Okay. So this is the problem given, and this is the curve that we have got. So we have one definition for the curve in this segment, right? That's the first one. And one definition for the curve in this segment, which is the second one. Which is why we say that the spline is piecewise defined. Meaning that if I had more control points, right, then I will have more segments, and each segment actually will have an expression like this, which doesn't look like the expression before. So these two expressions are very different, and you can imagine if I had more segments, 2 to 3, 3 to 4, etc., I will have different expressions. So that's the first thing. Right. Now, the second thing, the one that is easy for me to do, is to evaluate this curve at P at 0. So P at 0 means I have to evaluate it in the first segment because that's where 0 appears. And what do I get? The only non-zero term is the first one. And I get that. And then I try to find P of 1, sorry, P of 2 first. That is easier. Again, the first three terms are all 0 because of this term 2 minus u. They'll all drop off. The only non-zero term left will be P3. So what is this saying? That even though I have defined it like this, that points may or may not be on the curve, but the definition ensures that my curve will always interpolate the two end control points, P0 and Pn. Okay, I'm generalizing, but believe me, you can run other examples and see it. And of course, I will make an argument later as to why it should always be true. Now, the interesting thing, is that it is piecewise defined, which means what is happening at this junction, where I have a segment defined in this direction. I also have a segment defined in this direction. So I want to know what is happening here, right? So let's say I want to find P of 1, right? And I will put a minus sign here or the left here for the segment that is coming from the left, which is the first one, right? So if I put u equals 1 in the first segment, right, these two terms drop off and I'm only left with the last two terms, right? And that comes out to be P1 plus P2 by 2, right? 2 minus 1, and therefore u by 2, 1 by 2 and 1 by 2 here, and therefore the point is P. And if I were to calculate P1 from the right, then it is the second segment that I need to evaluate at u equals 1. Again, the last two terms drop off. This and this term drop off because of the u minus 1. And if I evaluate these two, right, again, I get P1 plus P2 by 2. And so that's the nice thing about the B-spline. That even though it is piecewise defined, right, you have continuity. In fact, you can, I'm not going to differentiate this, but if you differentiate this, you will find that Pu at 0 will be, if I'm not mistaken, 2 P1 minus P0, and Pu at 2 will be twice P3 minus P2. Okay, therefore, my curve, B-spline curve, even though it is defined in number of segments, right, ends up looking like this. So the first segment starts from P0 tangential to P0, P1 and goes off to P2, and the second segment does that. Slightly bad drawing, but if you look at the tangent at I need some space. Let me first locate my mouse and create the space here, right? I have not found Pu at 1, and you will find that that is equal to P2 minus P1 on both sides, from the left and from the right. Okay, again, I am not deriving this as a general property. I am showing you with an example, but there are other courses where you can, see how this property has to be the way it is. Okay, so that's very interesting now, right? That my curve, even though it is piecewise defined, right, it gives me continuity up to k-1 order. Okay, this is a shorthand notation. We will see a more formal definition of these, but essentially it says the derivative up to which the curve is continuous. Okay, so C0 means points, there are no break in the curve. C1 means tangent, right? Derivatives are continuous, first derivatives are continuous. C2 means that curvatures are continuous and so forth. And so that if we have the spline curve, right, then we find that even though the definition is piecewise, meaning each segment has a different expression for the curve, continuity is automatically ensured. Okay, so that's, I mean, I have, as I said, again, I reiterate this, I'm showing it to you as an example, but you should take it as the thing. And of course, the other thing that we have showed here is that the curve starts tangential to the first polygon leg at the first control point and ends tangential to the last polygon leg at the last control point. Okay, so now let me just point out one more thing before we go back to the slides, right? And that is, remember we said that the k value can go from 2 to n+1, right? So here n is equal to 3, correct? So I had these 4 points, so n is equal to 3. So supposing instead of choosing k as 3 in the previous segment, let's say I choose k to be equal to the largest that is possible, which is 4. Right? What is the not vector in this case? There's no trick here. You just have to follow the what we said. It is first k terms are 0. Right? The last k terms. First of all, how many terms will we have? N plus k plus 1, right? 4 plus 3 plus 1, so 8 terms. But there are, first 4 are gone. So the last 4 in this case now are n minus k plus 2. And what is n minus k plus 2? So that's the not interval, not vector, sorry. How many segments are there? Okay, so in this case, the spline has only one segment going from 0 to 1, all the way from 0 to 1. So there is no segmentation here. There is only one segment all the way from 0 to 1. But these properties will remain, meaning it will take off tangent to the first polygon leg and interpolate the first point control point, and it will arrive tangent to the last polygon leg and at the end at the last control point. What curve is this? What curve do you know which will start interpolate the first control point and be tangential to the first polygon leg and end at the last one and be tangential to the last polygon leg?
Bezier.
Bezier, yes. That's the only answer we have right now. It can't be anything else. And therefore, now we conclude that the spline, right, is a general form of the Bezier, or alternately, Bezier is a special form of the spline when k equals n plus 1. Okay. So that's the statement that we want to conclude from this derivation here. Okay, two things that we have done. One, that my definition of the spline is piecewise, but I don't have to worry about because I get continuity. Sorry, I made a mistake here. This should be k minus 2. You have only tangent continuity here. So ck minus 2 continuity will always be there, meaning at the naught intervals, right? So in this picture here, at this naught, right, which is 1, I will have point continuity and tangent continuity guaranteed. You don't have to do anything at all to get that. That's point 1. The second is that when I choose k to be the extreme or the max that I can choose, I end up getting the Bezier curve. So which means the Bezier case is a special form of a special case of the B-spline for k equals n plus 1. Okay, that's the summary here. So I'm going to switch back to the slides now. Let me do that. And then go down, right, to... Actually, I was trying to do it here and I found that I don't have space, and so I gave up and went there. Now, because your spline is a general form of the Bezier, or the Bezier is a special form of the spline, you would expect that the properties that you see for the Bezier will automatically be also satisfied for the spline, because it is more general than the spline, right? So the first, of course, is what we saw. Curve is of the order k, degree is k minus 1. And the second was very important. You have k minus 2 order of continuity, even though it is defined piecewise, right? So if your k is 4 or a cubic, then you can expect to have curvature continuity automatically there at the junctions of the segments. And the B-spline is the Bezier curve for k equals n plus 1. And lastly, of course, that all the properties of the Bezier curve. We've already seen 2, right? The endpoints, interpolation, tangent to the first polygon, second polygon, like all that is already satisfied. But the interesting thing with the B-spline is that the convex hull property is satisfied. What was the convex hull property? That the curve will always lie inside the convex hull of the control polygon, right? Let me see if I have a good picture somewhere. Okay, we can just use this here, right? So, so you can see that if I look at the control polygon here, the convex hull is this. Okay, that's the convex hull. And so the curve is guaranteed to lie inside this. Even after the curve point has moved P2 here, the new convex hull will look like this, right? Imagine the snapping rubber band. As I said, it will stop at all the outermost points, and therefore it will stop at 3, this, 2, and that, right? And the curve is inside that. Now, the nice thing about the Bezier, right, is that not only does it satisfy the convex hull for the entire curve, but there is a tighter convex hull property that the Bezier's B-spline satisfies, which is that each of the segments, right, each of the n minus k plus 2 segments, right, lies inside the convex hull of the k points defining that segment. Okay, so which means k was 4 here. So the first 4 points are 1, 2, 3, and 4. And so that's the first segment. So this is the first segment, and it lies inside this convex hull. Then the second curve will be defined by 1, 2, 3, and 4. And so that segment will lie inside this control polygon. And where is that segment? There. Where is that? Oh, here. I think that is one of the endpoints. Huh? And then because this point is appearing to be a little lower. So that must be the next segment. So this is one segment here. And then, likewise, you will get for each of these that the curve will lie inside the convex hull of the K control points that define that. Let me see if I can draw it on this. Because here the curves are better marked. So K is 3 here. So the first convex hull of the first K points, first 3 points is this, and this segment is inside that. The second one is this, and that is satisfied. And the third one is that, and that is satisfied. And the fourth one is that, and that is satisfied again. And the fifth one is this, and that is satisfied. And the last one is that, and that is satisfied again. So that's very powerful, and much tighter convex hull property than you had for the Bezier case. Right? And so now I have a question for you, which is that the other extreme that we talked about for K was 2. Right? We have seen what happens at K equals n plus 1. You get the Bezier, but K equals 2. What is the curve that I will get? So let's take the same example here. This curve here, right? What do you think will be the curve for K equals 2? I'm trying to see if I can erase this, and so I can draw the result for the next one. Yeah, while I'm doing this, please tell me the answer. What is the curve? I mean, we had mentioned that it is going to be a line, but I want you to draw the line, or tell me what line I should draw here. So K is equal to 2, right? Which means how many control points define each segment? Come on. At least someone should answer that. How many control points define each segment? Don't let me have lost all of you. Let me just see if everybody is there. Hang on. I hope I'm not speaking to internet with nobody there. Well, people are there, it looks like. There's been a drop since the beginning, but any answers? We had said that each segment in my curve will be defined by K control points. So if K is 2, then I'll have only 2 control points defining each segment. Right? But we also now have a property that the curve, each segment of the curve will lie inside the convex hull of the control points that define that segment. So what is the convex hull of 2 points? So if I have 2 points, what is the convex hull? The line joining the 2 points, right? And so what will the curve be? So the first 2 points will define the first segment. That is that. Second 2 points will define this. Third will do that. Fourth will do this. Fifth will do that. Sixth will do this, and seventh will do that. Okay. So what has happened? That for K equals 2, you get the control polygon back. right? And for k equals n plus 1, you get the Bezier curve. And everything else is in between. So you start as k increases, you tend to get more smooth and smooth curve as you go forward. So that is, I think this curve is that example only. Only thing is it is a little too close to 8. I don't like that, right? But you can see here that this has got so many segments, right? So 1, 2, 3, 4, 5, 6, 7, 8 segments here. Whereas here, there is only one segment, between all of these 8 points. Right? And so that's the variation. And for the lowest order, where k is equal to 2 degrees 1, I would have started with the control polygon. In this example that we were looking at here, right, the Bezier might be more shallow than any of these curves because it has to go off like this and maybe come back like that, right? So the first one is this wriggly one. The second one is a little less wriggly than that. The third will be less. And finally, you get this sort of a smooth, less undulating Bezier curve. OK, so that's the spline curve. You have the properties now. I mean, you know how to derive it, though I'm not expecting you to generate all these curve segments using those expressions, but you know all the properties that it has got. OK. So now I have a question for you, and with which I will stop and we'll answer it in the next class. And the question is the following, that all this while we were looking at, you trying to define curves for which there were no analytical expressions already available with you. Right? Now what I want you to do is tell me what the control when the spline or the Bezier representation will be for a quadrant of a circle which is centered at the origin and is of unit radius. 90 degrees. OK, so I want to know what P of U is. OK, I'll stop here and we'll pick it up in the next class, that is Monday. If there are questions on the material covered today, then you can raise them first and then we will start from this point here. OK, yeah.
Sir?
Somebody has, yeah, go ahead.
So is this the assignment or this?
I mean, you can treat it as an assignment, but it's just a question.
Oh,
it'll be nice if you can try it and give an answer in the next class. Yeah.
Yes. Thanks.
OK. Yeah. Thank you. OK, so I'll see you folks on Monday. Yeah. Thanks.
Thank you, sir.
Thank you.
Thank you, sir. Bye.
Thank you. Yeah. Bye.